Thanks for the introduction and thanks for having me. As said, I'm just going to talk about like a very elementary proof of this inequality that Dan said this morning and originally proved by Biane, Capitaine, Guionnet. And then the proof I'll be talking about is a joint work with David Jekel. Okay, so throughout the talk, I'm going to fix a bunch of stuff, right? So the usual things, M, tau, tracial von Neumann algebra. We actually do this for a relative version, so I'll also fix separable subalgebra, separable von Neumann subalgebra, generated by a tuple y, generated by some possibly infinite tuple y.
What's a separable subalgebra?
Separable meaning the length of my generator is countable. Yeah. So maybe I'll write like yj, j and n, something like that. Okay. Okay, and then I'll also actually, for most of the things that I talk about, fix some microstates yn, microstates for y with uniformly bounded operator norm. Yeah, and this isn't a loss of generality, and we prove this in the paper. But for most things I'll be talking about, all these things will be fixed. Yep. Okay. Cool. So we've already seen the definitions of microstates and non-microstates for entropy, so I will not go through them in detail. But because I'm doing like a kind of relative conditional version, I'll just make some comments. So we have these microstate spaces for some neighborhood O. Every time I write a neighborhood, this is a neighborhood of the law of some xy, where I should fix my x's, fix some tuple x. This is from my von Neumann algebra. M of them, whatever, self-adjoint. Okay. Great. Then my microstate spaces are going to condition upon these fixed yns converging to y, and it's exactly what you think of. It's all of the n by n matrices xn with operator norm bounded by r, so that the law of xn yn is in this O neighborhood of the law of xy. Okay, so once you make that definition, then you can do the same definition of chi. So ... do all of your limits, except, do I want to do this? I think I need it for proofs later. Okay, so you do all the usual things, except I have to do this relative to an ultrafilter. If you don't know what that is, every time I talk about some ultralimit, just replace it with lim sup or some subsequential limit. The proofs will work the same, just like for the details of something that I'll do, I'll need this u once. Okay. All right. So this relative microstates free entropy is defined in the same way as the usual microstates free entropy. You take some infimum over neighborhoods of this law, and then this ultralimit you can replace with lim sup if you would like, of 1 over n squared log volume, usual stuff, blah, 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 gamma.
Can you clarify what this notation means when you condition on yn with the squiggle to y? That didn't appear in Benstock, right?
Right. Yeah, so I mean that when I choose, yeah, maybe it will become clear if I actually write down the definition of this. So by this, I mean all xn, mn, C, self-adjoint, M tuples, whatever. So that, okay, first of all, operator norm bounded by R, and the law of x and yn is in O. So this is what I mean. Like I fixed some microstates for this generator of a subalgebra, and I'm just saying that you look at microstates xn for x, which also agree with these yns.
The fact that you have a countable rather than a finite number of generators for A is not a problem.
It's not a problem. Okay, all the usual stuff.
Formally, it's the limit as right. I mean, as you increase more and as you throw in more and more of the Y family, that's what you mean, right?
Yeah.
I mean, the notion of a law for an infinite family is not really well defined. So what you, at the time that you compute entropy, you throw in more and more of the Y's, and then you take the infimum as you do that.
I guess I'm confused because this always a neighborhood means a weak star neighborhood, right?
Yes.
So you fixed a finite number of elementary sets. Right?
Yes.
So there's only a finite number of polynomials, so they depend only on a finite number of the Y's, right?
Yeah, for each neighborhood, this will only depend on a finite number.
So this object doesn't actually depend on the infinite sequence. There's always, for every O, there's a finite number of these Y's that appear in the definition.
Yeah, but as I take the infimum over neighborhoods, it will depend on a countable.
Yeah, the infimum over, sorry, where's the infimum?
Right? Sorry, here.
Right,
Yeah,
okay.
yeah.
So that's
but for
where
a fixed O, it's true. This is only depends on finite
very
number things. Yes.
But the point is that you fix the approximation for Y's.
Yeah, this is important.
the approximation for all O, you have the same approximation for the Y's.
Yes, I fixed my
You
microstates.
fixed your approximation.
Is this quantity independent of the choice of Yn?
What a great question. Yeah, so this quantity actually, if you look at it in our paper, we don't write it with the YNs, we write it with an embedding, and it's independent of the YNs if the YNs generate the same embedding into the matrix ultraproduct.
So,
A priori, right?
for instance, you're talking about my definition
Yes.
in my paper. There's a trick, which is, of course, you take the soup over all
Yes,
possible
yes.
Sorry, soup over all possible Y's.
Yeah.
But then the point is that if since the Y's generate an amenable for Neumann algebras, if this A is amenable, then all such Y's are intertwinable by unitary. So then it doesn't matter.
Like what that was done.
Yeah. So a priori, this depends on this choice. You can soup over both of them and recover the relative entropy from Dima's paper. Yeah. Other questions? Okay, but it will be nice for me in proofs to just like fix the sequence of microstates. Makes life easy, right? Okay, great. I'll actually also need the definition of the non-microstates entropy, but I think I won't need it until the last proof, so maybe I'll just give it then. All right. Okay, so I claimed that I had some nice elementary proof of this, and it just relies on relating all of these quantities back to the classical entropic things of the matrix microstates. So proposition, and I'm going to call this M for microstates. And it's the following: this quantity with this ultralimit, depending on these fixed YNs, is the supremum of ultralimits of classical entropies of just my matrix microstates. Here I'm writing HN. This is just a matrix renormalization, so that my limit actually works well, right? So it's just like a 1 over n squared of the classical entropy of my xn's plus this m log n. Okay, over nice sequences of xn's. Over all sequences xn satisfying the following three conditions. One, obviously, the law of the xn's and the yn's has to converge to the law of xy in probability. Two, there exists some R so that my ultralimit of the 2 norm of the xn's, operator norm is at most R. Okay, in probability, and then 3, the 2 norm of the xn's decay exponentially outside of some compact set. And this is uniform. Yeah, uniformly in N. Okay, great. Okay, so let me sketch maybe the proof of this proposition. One direction's really easy, right? So if I want to say that this limit of classical entropies is at least as large as this relative free entropy, this is fairly easy, right? I just need to choose some xn's that get really close to realizing this, but this in particular is defined to be some infimum of some log of volumes, and so I'll do it in the following way. Take some nested decreasing neighborhoods, OK, which go down to this law. And then define the indices where this gets 1 over k close. So set AK to be the set of all indices bigger than or equal to k, such that the thing used in defining this relative entropy, log volume gamma R N O. OK. With the normalizing factor, fine. OK, is at least 1 over k close to this infimum. X given the stuff, minus 1 over k. OK, of course. Thanks. OK. And then, I mean, this construction is almost basically by definition. Yeah, so now take xn uniformly from these gamma sets. Maybe I'll give these a name. SOK, all right, from SOK for n in AK minus 1. OK. OK. Yeah, so I basically, because this quantity is realized as an infimum of such things over neighborhoods, I can always find indices, like this set is non-empty, and are also nested decreasing, and then I can just like choose the right xn's to make this happen. And in particular, the xn's are also nice, right? Unitarily invariant and uniformly bounded in operator norm. That will be nice later. Yes? Take xn to have the uniform distribution from this microstate space for these indices.
What's the measure on matrices?
Sorry?
What's the measure on? Is it the Lebesgue measure on?
Yes.
Okay.
Yes. OK, other inequality. Great. So less than or equal to. And this is kind of, I guess, like a somewhat standard trick from proofs of this without the conditioning. Yeah. OK, so for the other direction, you use the following fact, that if you have some partition, measurable partition of your relevant space, I guess in our case this is this, then you have an inequality involving your entropy in terms of the partition, right? And maybe I don't actually care about what this inequality says, what the actual form of this is, but some quantity involving Lebesgue measure, your law of your xn's, and these sj's. Some term goes here. It's not actually important to me what the term is, because I won't go into details of the manipulation on that part of the algebra. Sorry. OK. So great. You use this measurable partition, and then you look at the following thing, right? So for a fixed neighborhood O, you look at, you've got your gamma R, O, yn converging to y, some blobby boy, whatever. And within this set, all right, maybe I do have to write what the term is. Within this set, the term here behaves nicely because you know that all of the microstates in this set are going to converge as I send the dimension off to infinity. And so the term you get here from this is going to approximate your chi-u, your microstate's relative free entropy. And then outside of this, you just have to show all the nice decay that you want happens. And so you have some annuli outside of here. And in particular, you choose the annuli based on the size of like the ball, the compact ball in which this compact set lies. And so outside of that, you get this exponential decay. And then you can just like bound all of these error terms on the annuli, and they go to 0. Nothing complicated is going on. I'm not going to like write out all the details because it will be boring for everyone. But those are the broad strokes of the proof of such a thing. Questions before I move on? OK, cool. I think I'll leave this up. And I'll also leave this up, maybe. I don't know if I'll need them later. OK. So, oh, there's more things. All right, I promised that I would need some facts about the non-microstate side, and then I can combine everything to prove the final result. So on the non-microstate side, well, first I'll need this thing that no one has written down, but maybe everyone knows. Just in case everyone doesn't know, I'll write it anyway. Dan said this in his talk this morning. You can recover the entropy via an integral from the Fisher information. In particular, this chi star of x given y is this kind of integral m, the length of my tuple x, minus this free Fisher information quantity. What am I using? T to the 1/2 s. And then some normalizing term, right? OK. OK, here sorry. OK, all right. Here my S is a freely independent semicircular element, so I'm just doing some Brownian motion in X and then taking some appropriately normalized integral, and then I get this non-microstates free entropy. And this guy is my free Fisher information. In particular, B star of x given y is the 2 norm of some conjugate variable. And I'll just need this briefly in a proof, so I will write it. So satisfies this type of integration by parts formula. For every non-commutative polynomial in m many variables, this conjugate variable satisfies this thing. Great. OK.
So the polynomial here has coefficients in y? Is that what relative to y?
Yeah. I have polynomials. Again, it's like I have infinitely many y's, but every polynomial uses only finitely many of them.
Andrew, maybe you call it d sub xi. That'll be clearer. That is the partial with respect to xi.
Yes. OK. Great. So I have a prop m, and I have a prop nm, non-microstates proposition. All right. M, tau, x, y, yn, all as before on the board that is conveniently hidden. Now, in this case, I want to say that for every, again, like nice matrix tuple related to my x, I have some nice inequality relating this free Fisher information back to classical Fisher informations. So suppose xn in the right space is a sequence of microstates for x such that what do I need to happen? Oh, I actually don't even just need a sequence of microstates for x. It needs to include y, right? So such that, you know, the law of xn, yn converges to the law of xy. And you have some moment boundedness condition, which maybe I don't actually care to write down. So there is some moment condition here. But what's the point of the moment condition? Moment condition. The point of the moment condition is exactly what Benoit was talking about earlier in his talk, the fact that whenever I look at expected values of traces of objects, they behave how I would like them to behave, right? So the trace of polynomials in x and yn, all right, great, actually converges to the thing that I want it to. Yeah, this isn't actually one of the assumptions, but the moment condition implies this, and it's the thing that you actually need. OK. Unfortunately, I now have to write this in this little space.
Sorry,
Yeah.
I'm confused. What's the meaning of E?
Expectation.
Expectation, but xn's are microstates, right? So
Yes.
I understand. What are you, with respect to what randomness are you taking into expectation?
These. Oh, you're saying this is fixed? No, no, no. Yeah, maybe this is me having poor language.
Oh, a sequence of random, I see.
Yeah. A sequence of random variables such that this happens, yeah. Otherwise, the moment condition wouldn't make much sense either. OK.
So, but I don't understand, what does it mean now that the law of x and y and converges? I just don't understand the difference between the second line and the last line.
The second line.
Well, you're saying that the law of x and y and converges to the law of xy, but then isn't that the
Yes.
same as what's down below?
Oh,
There's
no, this is my fault again.
Xn's are not assumed to be uniformly bounded.
No, I mean there's finitely many of. Oh, uniformly bounded in n. No. This is my fault. What I need to write in probability here, and I mean the moment condition lets me upgrade to almost sure.
That's not almost sure. That's an L1.
Sorry. Yeah.
But isn't that weaker than in probability?
Strong.
Is it?
Well, no, it's
No,
neither.
it's on
It's neither.
average.
It's neither.
It's neither, yeah.
Okay.
Expectation.
No, it's stronger and weaker, right? Because it means it's L1, but there's no consideration.
Oh, right. Yes.
Okay. Then this phi star, my free Fisher information is at most the lim inf, or sorry, you can replace this with the lim inf if you'd like. The right normalization of my classical Fisher informations of my matrix models. Okay, great. All right. Ooh, okay. Let's prove this. Or sketch it at least, it's not difficult. So first of all,
ask the bottom right limit of first 1 over n to the something, or is
what's your question? This is a 1 over n to the 4.
To the 4, thanks.
Should it be squared?
My normalization has to do with the normalized trace, and this means that it's different from the usual random matrix normalization by a factor of root n, and then you end up getting this. Yeah. Okay. So
Go on, can I just ask, because I got a little bit lost in the notation. So what exactly is the role of this Neumann subalgebra A and the microstates Y? Like, why do we need those?
It's just a slightly more general result. I could do the whole talk without the y's if I wished to. Maybe I should have. Yeah, you're just saying like, I know all the information about some separable subalgebra, and then I want to talk about the entropy of my tuple with respect to this subalgebra.
The point is you're just proving something more general than what you wrote on top there, right?
Yeah, only slightly. It's just like, yeah, only slightly.
So we can ignore these y everywhere, and we would have a proof of the ordinary chi less or equal,
Yes,
right? Okay.
yes. You can make y an empty tuple, yes.
So it's not like you need the a, non-trivial a, to complete the
No.
first.
Yeah. Okay. If the right-hand side is infinite, this fact is silly, so we'll assume that this guy is finite. The point of it being finite means I know enough conjugate variables exist. In particular, for many, if you're thinking about this as some lim-inf instead of some ultra-limit, then I'm saying for every n, there exists some bigger thing so that I can find a conjugate variable. But for me, I'm just going to say for ultrafilter many n, there exists some conjugate variable. So that you have, I guess, yeah, n is fine. So that you have the following behavior. This inner product is with respect to normalized trace. I do divide by n here. Oh, I divide by n. Yeah. Okay. Okay. Great. And then this ends up being the same as if I take this trace tensor trace of partial xj of p. X n, y n. Okay. Great. Okay, and then you need the fact that phi of xy is actually realized as a soup of the following types of objects. If you take tau tensor tau of partial xj, px, oh, yeah, xy. And the supremum is over polynomials whose norm is at most 1. And I want this for just partial x. Okay. This is not hard to see. It's really just like some algebraic argument, and you do like a little bit of Riesz representation. I'm going to black box this. It's a lemma. Just believe me that it's true. And after, sorry?
It's just the same as the definition of the norm of Cn, right? I mean, if you just, you know,
Just using the density of the polynomial.
just using the...
Yeah. That's fine. Okay. Okay.
Maybe just if you just say that that expression is equal to the dot product between C and P, that clarifies why that's true.
The dot product between C and E?
And P.
P. Oh, yes, that's fine. Yes. Okay. Great. Okay. All right. After this, it's super simple. I'm just going to look at this term. Because I know that my moment condition means that this thing behaves well, I can write this as a limit of expected trace of, all right, the right polynomial in x and yn. Okay, this thing satisfies my nice integration by parts with the 1 over n squared thrown in. In particular, I can use this equality and then Cauchy-Schwarz over here, and I end up getting this 2 norm of whatever my polynomial is, squared. Okay, whole thing has to be to the 1/2, fine. And then because of this term, which ends up getting squared when I do Cauchy-Schwarz, I get my claimed free Fisher information. Okay, And now just remember that you're taking soup over things with normal y.
There's a half missing from the beginning, I think. It's the square root of the Fisher information that you're writing.
Yeah, there should be a
No, or just put square root on the Fisher so that you don't have to do it.
Sure. Sure.
And there's an inequality, I think, right? Because
Cauchy-Schwarz gives me an inequality, indeed. Of course. Okay, great. Okay, so this proves my prop NM, and then I can use the confluence of these two things to write a very short proof, modulo, okay, a bunch of algebraic work that I won't do. But I claimed it was elementary, and it is, indeed. Okay. All right. So theorem, whatever, with the ultrafilter or not, it doesn't matter. You can soup afterwards. This at most, this non-microstates relative free entropy. You can get rid of the y's if you like to. All right, proof. So first of all, note that my assumptions are satisfied because when this guy is not minus infinity, if this guy is finite, then I have some matrix microstates to work with, and I can, so like this guy gets satisfied, and I also have, sorry. Yeah, I mean, this is the important one. Oh, in fact, when I proved this, right, in one of the directions, I just chose microstates uniformly out of the microstate space, and so they satisfy all of these nice properties, and then it's easy to check that they satisfy whatever this moment condition is. Okay. Set S to be some M tuple of freely independent semicirculars. And Sn, an M tuple of independent GUEs. Okay. We can apply proposition non-microstates to, so apply prop NM to this Brownian motion starting in X and also my Y. And you get the inequality that you care about, right? X plus U to the 1/2 S. There's no given, sorry. Less than or equal to. There is a given, sorry. Okay, this ultra limit of Fisher informations of my xn's. Okay, and then looking at my definition of what my non-microstates free entropy is, I know that I have to do some integrating. So I'll do that, but for the sake of being able to do arguments, I'm going to do it on a bounded interval first and then send t off to infinity later. Great, you do this and you also include my, my 1/2 term, just so that I can use the classical fact that this recovers, this side recovers my classical entropies of some microstates, 1/2 Sn minus Hn Xn.
U should be T.
T, yes. And I still have my limit. And if you work through this, I still have my 1/n to the 4. Okay.
This time around should be squared, I think.
Sorry?
This time around should be 1/n squared.
I won't go through this now, but I'm fairly
So it's
certain.
1/n squared because of the normalization of the Brownian motion. So it's should be well.
But h to the n is
But-
normalized too.
Yeah.
Yeah, sorry, okay, I'm sorry.
There's a lot of normalizations running around. It's not important. I mean, okay, I'm not going to actually do the algebra, and so it's not important what the 1/n to the 4th or the 1/n squared is doing. all I want to do now, okay, so now I've applied proposition non-microstates. Now I want to apply proposition microstates, right? So you do some algebra, you isolate this term, whose ultralimit will end up being chi, the microstates relative entropy. And then you apply that, right? So now with my microstates proposition, I can say that this guy is limit, okay, well, less than or equal to, because I have to take soups. But that's fine. It's the right direction of the inequality anyway. Hn, xn. And isolating this guy, this is Hn of this Brownian motion, is t to the 1/2 s, minus this integral, right? 0 to t v star. Okay, after this, you bound your first term, this guy. You bound your first term using the fact that entropy is controlled by variance. Variance of whatever the argument is. And then you just do a bunch of like baby calculus, algebra stuff, and everything works out, and you get chi star over here. You recover exactly this integral formula after doing all the baby calculus, which I won't do. Yeah.
Why do you need that entropy is controlled by variance?
Sorry?
Why do you need that entropy is controlled by variance?
Oh, I just mean the general upper bound, right? Like there's a general upper bound that the classical entropy of any random variable is less than or equal to, I don't remember the constants that go in front, and then the variance of the argument.
Why do you need it? Where does it go into the proof?
So the next step in the proof is going to be less than or equal to whatever this variance upper bound is, minus blah, blah, blah. And then there's going to be a little bit of cancellation. There's going to be like a log 1 plus t minus a log of t, and then I send t off to infinity, whatever. That's not important. The point is I don't need this term, right? I need some integral of m over 1 plus t to appear, and I need this term to appear. And they appear from this entropy bounded by variance.
So at some point you have to use critically that for the Gaussian, right, the entropies are the same. The limit of the Shannon entropy is the same one. So somehow what you're doing is by increasing t, you are interpolating, you're somehow getting this Hn plus t1/2 s, you're getting closer and closer to just being Gaussian, or semicircular in this case, and Gaussian on the other one, right? And so at that moment, you're just approximating it with a rough approximation with just the second moment, which is the Gaussian bound.
All right. This was all I wanted to say about this elementary proof. Thanks.